So we have Alice, Bob, and Carlos. They're playing soccer. We saw 4 episodes of soccer. Like, imagine you're a talent scout, right? You're coming to the amateur soccer game, and you're going to recruit some of these players to be on your professional team. Oh, doesn't Guelph have a team now? Okay, well, I don't know. Let me stop pretending that I know what's going on with the soccer. Okay, so we see these 4 things happen. First, Alice passes to Bob, and then they don't score. Carlos passes to Bob, and sometimes they score, and sometimes they don't score. The first thing that I asked you to do, which has absolutely no ambiguity in it, is exactly to apply the Monte Carlo algorithms that we have been doing before. Last time we put them on the computer. If you only have 4 episodes, you should be able to figure out these values exactly using the algorithm. So that's the Monte Carlo estimation procedure that we talked about before. And let's see what you said for those. And once again, this is just applying the algorithm. So there's one actual right answer to what the Monte Carlo value is. Let's see what you guys said. Okay. So for Alice, people put in 0. 12 people put in 0. The value of Alice is 0, which is kind of a rude thing to say to Alice. But that is perfectly correct. So in the Monte Carlo algorithm, you look at all the times you visited that state. We visited this state exactly 1 time. And in that universe, we scored 0 points. So Alice is 0 points because every time Alice had the ball, we ended up scoring 0. Very good. What about the other 2? Maybe you did the other 2 also correctly if you got Alice right. So Bob, people put in a half for Bob, which is exactly right. There were 4 episodes with Bob. Bob got the ball every single time, and half the time he scored, half the time he didn't score. So technically it's 2 out of 4, which is the same as a half. So also very good. And last but not least, Carlos. A little more spread out, but again, 2/3 is the right answer. There are 3 episodes where Carlos has the ball. So there's 3 things we're averaging, and in 2 of those universes, we scored, and in 1 universe we didn't score, so 2 out of 3. So that's perfectly correct. So very well done. You guys understand the Monte Carlo algorithm. That's a good warm-up. Today, what we are doing is we are going beyond the Monte Carlo algorithm, and to motivate what's going on, we're going to have this discussion of what we think about Alice. Do you think the Monte Carlo algorithm is underestimating or overestimating the value of Alice having the ball? So once again, the value of Alice having the ball, according to Monte Carlo, is literally the number 0. But now I want you to use your human judgment and tell me, do you think Monte Carlo is underestimating Alice or overestimating Alice or correctly estimating Alice? And you guys said, I think the Monte Carlo algorithm blank the value of having Alice correctly estimates, overestimates, or underestimates. Wow, unanimous. Amazing. 15 out of 15 people said they are underestimating Alice. Does someone want to tell me why they think it's underestimating Alice? Yeah.
Alice did get the ball to Bob.
Yes.
And he has a value of 0.5.
Uh-huh.
So probably multiply the probability that it gets to Bob by his probability.
I see. Okay, so you're saying we know actually something about Bob, which is he scores about half the time. And we know that because we have all these samples with Bob. So we're pretty sure that Bob scores about half the time. What do we know about Alice? The only thing we actually know about Alice is that she passed it to Bob, right? And she did that 100% of the time. She never dropped the ball. She didn't ever pass it to Carlos, anything like that. The only thing we saw is she passed it to Bob. And therefore, we should say that because Bob has a value of a half, Alice has a value of a half too. Is that a fair paraphrase of your argument? Okay, very, very nice argument. Anybody else have another way to think about it? Or why did you say underestimates Alice? Yeah.
Too small of a sample size?
Yeah, too small. Okay, this is a great point. So I agree it's a very small sample size. Can you tell me why a very small sample size leads to underestimates? Like, why not overestimates? Okay, yeah.
I guess it could be overestimate too.
Okay, yeah. And, okay, I guess I kind of set you guys up a little here because I said that it's a soccer game, you score 0 points or 1 point. So maybe you could think that 0 is the lowest possible. And then, of course, if we estimate Alice at 0, then that must be an underestimate because that's the lowest possible. But actually, you might score on your own net or something. Like you could get negative 1 point. So Alice, it could go quite a bit lower. So it's true we don't have a lot of data. In statistics, there's a special word for not an overestimate and not an underestimate. Does anyone know this special word? when you don't overestimate and you don't underestimate. You're wrong, but on average, you're exactly right. You're not over or underestimating. It's a very silly word. It doesn't mean what it means in English. Who's taking this test? Yeah, okay.
It's not unbiased.
Unbiased. It is unbiased. So the word unbiased is exactly what I would call correctly estimates, right? So underestimate would be like biased downwards. Overestimate is like biased upwards. Of course, in real life, when you say bias, like on the street, this is not what you're talking about. But this is what they're talking about in statistics class. And so I'm asking, in a statistics sense, it's true we have a very small sample. So our value for Alice is likely to be quite wrong. But on average, is it right? So given what we know, if we were to continue, on average, if it would either go not up nor down, then that would be unbiased or correctly estimates. If you think as we get more data, you think it's likely to go up, like more likely to go up than down, then you should vote for underestimates. And if you think it's more likely to go down, then you think it's an overestimate right now. So it's true that we have a small sample, and that as we get more data, we're going to definitely get a more accurate answer. But having a small sample size doesn't on its own tell you which of these cases it is. So it could be that you think it's going to go up, it could be that you think it's going to go down, or it could be that you think it's on average right and it will equally likely go up and down, or on average not change. So that's a good point. I think that's like an orthogonal issue, is the sample size, that's like how accurate you are. This is asking me which direction it is. Great comment. Any other comments about this? All right, let me reveal my answer. My answer was, so you guys got these ones right, 0, half, 2/3, very good. And I also put underestimates. So 15 out of 15 people, 100% of the people said what I said as well. And again, I think if you look at this as real life, if you were a scout watching this game happen, you would see Alice pass the ball to Bob very nicely, and you'd say, Alice did a great job in her role getting the ball to Bob. So like, why would we give her 0 points? Just because she got unlucky, and that time Bob didn't happen to score. And this idea is going to improve our Monte Carlo algorithm. So the Monte Carlo kind of has this bad property that it only goes by what actually happened at the end of the episode. And it sort of, by doing that, it sort of ignores all the other information we have about Bob, right? So it's like we have these 4 episodes to work with. And we said, when we're learning about Alice, we're going to ignore 3 out of 4 of them, because Alice only had the ball in the first one. But of course, we can do better as humans. We can see that Bob having the ball, we can use all 4 episodes to learn about what Bob does. And then we can use this one episode to see that Alice passed the ball to Bob. And that way we can get like an improved estimate. So that is the core idea here. We're going to try to improve the Monte Carlo by using something we know about Bob to learn something about Alice. And that's going to help us out. There is one more advantage of this idea. So our idea is, let's use just this transition to help us out. And the other big advantage is, imagine if the game was very, very long, and instead of going directly from Bob having the ball to scoring 0 points, imagine that a whole bunch of 1,000 things happen, and then something either scores or not scores, which is like a real life soccer game. You don't normally score immediately. Usually a lot of things happen first. And the advantage is you don't have to wait until the score happens to learn something. So just by seeing Alice pass to Bob, you can immediately learn something about Alice. You don't need to wait all the way until the scoring happens or doesn't happen. So we're going to see that today. That's the topic of today's class. All right, we're going to do some more specific examples, but this example was to warm you up, and I think it's a great example to learn what the hell is the point of what we're doing today. We're trying to make it so Alice has a score not of 0, but of something closer to a half. Okay, questions or comments about any of that or this example? Okay, I'm going to warm you guys up with a little video, again from the same video series that I've been using, because right at the beginning, they hyped this up pretty good. So I'm going to also play it, and hopefully that'll hype you up too. Okay, here we go. By the way, when I play this, can you guys hear it at the back? Is it okay for volume? All right, that's good. Let me crank this up. So this is the textbook we're using, and he's reading from the textbook.
If one had to identify one idea as central and novel to reinforcement learning, it would undoubtedly be temporal difference learning. And that's coming from Richard Sutton and Andrew Bardo, some of the pioneers of modern reinforcement learning. So yes, I think this is worthy of a video. In fact, this is part 4 of my 6-part series on RL fundamentals. My approach will be to present temporal difference learning and the related algorithms of Q-learning, SARSA, and expected SARSA as the result of making a series of adjustments starting from Monte Carlo methods, which we're already familiar with.
Okay, and that's exactly what we're going to do. So we're going to start with Monte Carlo, and we're going to see like how could you improve Monte Carlo exactly in the way you saw with trying to be a little bit more charitable to Alice and trying to more accurately estimate what she's doing. And I'm going to start with literally an example from the textbook, which is, again, the same idea, but a little bit more specific, not this vague Alice Bob thing, something with a little bit more numbers. And we're going to do this example. By the way, this book is really fantastic, and it's free online, so I highly recommend you try out the book. It is a little bit technical, so it's nice to get the ideas first. But then once you have the ideas, you can go read it pretty good. So we're going to do example 6.1, which is called driving home. So each day as you drive home from work, you try to predict how long it will take to get home. When you leave your office, you note the time, the day of the week, the weather, and anything else that might be relevant. Say on Friday, you are leaving at exactly 6 o'clock, and you estimate it will take 30 minutes to get home. As you reach your car, it's 6:05, and you notice it's starting to rain. Traffic is often slower, so you re-estimate that it will take 35 minutes, for a total of 40 minutes. 15 minutes later, you complete the highway portion of your journey in good time. As you exit onto a secondary road, you cut your estimate of total travel time to 35 minutes. Unfortunately, at this point, you get stuck behind a slow truck and the road is too narrow to pass. You end up having to follow the truck until you turn onto the side street where you live at 6:40. 3 minutes later, you are home. The sequence of states, times, and predictions is as follows. Okay, so what is the point of this? There's a big story with how much actual time it takes to go, or how long it's been, how long you predict it will be, and how long you predict is left. So how long you predict the entire thing will be, and how long you predict from where you are. So of course, at the moment you're about to pull into your house, you're pretty confident it's going to take you like 0 minutes to get home, and so you have a very accurate estimate near the end. At the beginning, you have a less accurate estimate. So you predict 30 minutes, and it actually took you 43 minutes, and so it's sort of the closer you are to the end state, the more accurate you are. But you do have this idea of a prediction at any given time. I also think about this if you do like sports. When it's close to the end of the game, you're often pretty sure who's going to win the game, right? If it's like 2-0 in a soccer game and there's 5 minutes left, you're pretty sure the team who's winning will win the game. At the beginning of the game, when it's 0-0 and there's 90 minutes to go, you're very unsure of who's going to win the game. And there's all these like in-betweens between these extremes. For example, if it's 1-0 and there's 60 minutes to go, yes, the team that's 1 up is likely to win, but like, there's a chance, there's enough time, the other team could come back. So this kind of situation is pretty typical in all sorts of prediction tasks. There's some kind of like final time where the predictions are perfect, and as you're going, you can always make a prediction that'll be less accurate the further you are away from the house. Okay, so the simplest way to try to figure this out is to do a Monte Carlo. And there's a whole paragraph here, but I'm gonna just show you the one nice picture for what is going on, and the Monte Carlo is this way. It's this picture over here. So you have all these predictions for the total travel time, leaving your office, reaching your car, exiting the highway, going on the secondary road, being at home, and arriving home. And if you're a learning human being, at the end of the day, when you actually get home, you go, oh wait, I thought it would only take me 30 minutes to get home, but actually it took me 43 minutes to get home. So next week when I leave the house, I should keep in mind that it took me longer than I thought, and I will adjust how long I think it takes me to get home. So I'll say like, oh, I will move my estimate from 30, I will move it up by some amount, right? If you're into Bayesian stuff or like certain internet discourses, people call this updating your priors. So they say, I used to think it took me 30 minutes to get home, then it took me 43 minutes to get home one time. Now I think it takes me to get home. Where you have to go somewhere, like if you're really extreme, you'll say, oh, it took me exactly 43 minutes to get home. But it's less extreme to move up by some amount. And of course, we learned the constant alpha rule, which says you take the difference, you add on alpha times that difference. So for example, if you did an alpha of 0.5, that's a pretty big alpha, then you would move up halfway up this arrow. So you would start at 30, you would say, I'm gonna adjust my estimate to say it's 37 minutes. I think it's 37 minutes next week. If you had an alpha of 0.01, then you would just move by like a little bit, right? 1/100th of that arrow. And maybe over many, many weeks, you would slowly drift towards the right thing. So that's our constant alpha MC. It's how much you want to move along this arrow is the amount alpha, and you update all these things, right? So since it took me longer than all of my estimates, I move all of my estimates up a little bit. That's Monte Carlo. On the other hand, just like the situation with Alice, you can imagine that if you're driving home, you can learn something even before you get home. So imagine you're driving home, and all of a sudden it's raining, like before you've even gotten home. You're like, I should have looked outside and seen that it was raining, and then I would have known that it takes me longer. So you can actually learn something directly just from the next state. So when you leave your office and then you notice that it's raining, you can already update your prior. You can already make an adjustment. And that is what's going on in this diagram over here called temporal difference learning. And it's called temporal difference because it's sort of like the change in the time is what you learn about. So instead of saying, I'm going to leave my office and then wait until I get home and then update according to some arrow, what you can do is you can already update when you leave your office by what happened immediately after that. So you can already do this update, which is this kind of arrow. So when you reach your car, you thought it took you 40 minutes. So you can already say, next time I leave my office, I'm going to update and wait a little bit longer. I'm going to estimate a higher amount of time to go. Similarly, between reaching your car and exiting the highway, because the estimate went down, you can pull that one down a little bit as well. And you can see that you have a different sequence of arrows. Instead of waiting till the end, you wait until the next step, and then you immediately learn something about what happens based on your estimate of the next step. So these arrows are still pulling you with a constant alpha update to your beliefs, but the point is you don't wait until the end, you just immediately update. All right, this is exactly what we wanted to do for Alice and Bob. So in the Alice and Bob example, let's pull that one back up, if I can find it. We said we want to learn about what happens when Alice has the ball. Let's just immediately learn. Let's not wait until the scoring happens. Let's immediately learn what happens once they pass it to Bob. So as soon as Alice passes it to Bob, we can say, what is the value of Alice having the ball? Well, we're going to move it in the direction of Bob having the ball. And if we already have a good estimate for Bob having the ball, which in this case we know the estimate is a half, then we can say Alice, whatever we think of Alice should be moved towards a half, right? If you were doing an alpha equals 1, you would immediately move it to Bob. If you were doing an alpha equals 0.1, you would move it 10% of the way towards the value of Bob. And you hope that over time it converges. So this is the same kind of arrow diagram as is illustrated in this car example. Okay, so this is the rough idea of this temporal difference learning idea. Don't wait until the end. Just learn. As soon as something happens, you can learn something just by your beliefs on how your beliefs change. To give a more extreme example, if your brain only worked by Monte Carlo, if the only thing you could do is Monte Carlo, the only thing you could do is learn something at the end of an event, it would mean that you could never learn to not crash a car until you've crashed a car, right? Because you would crash the car and then you go, oh, geez, all those things I did were really stupid. It led to me crashing the car. But real humans, if you're like me when you were learning to drive, you had a lot of near collisions and you were like, wow, that was really close, right? You're like, geez, I really should have been looking in that direction. You didn't actually crash the car, but you got close to crashing the car. And at that moment you go, oh geez, I was close to crashing the car. Let's not even get close to crashing the car. So you don't need to wait for a car crash to learn something. You can wait until a near car crash happens, and then you learn from that, right? It's the same idea as over here. Don't wait until the end of the episode to learn something. You can learn something by how your beliefs change over time. If they're changing by a lot, that means that something is happening. This should ideally be one big constant. If you were a perfect estimator, it would all say 43 minutes. But it's not, and that's reflecting that you didn't estimate things perfectly. Yeah?
So let's say you're going from leaving office to reaching car.
Yeah.
And between the Monte Carlo versus this temporal difference thing.
Right.
We're updating the reaching car, or like we have information for what the estimated value should be at reaching car. So
Yeah.
we're estimating some value from that to leaving office. But for reaching car,
Yes.
we're estimating that value. Isn't that based on what the actual outcome is?
Well, okay, so in this example, right, this is not our first day driving home from the office. So we have some kind of estimate already. And so the estimate of coming up with why do we think it takes 40 minutes once we reach our car to get home, it's because we have some experience and we have some prior belief that it takes 40 minutes. And the point is we can use the prior belief at 40 minutes. That's a more accurate estimate than we had at leaving the office. So we can update our belief at the leaving the office time because we can push it towards the more accurate estimate of reaching car. So it really is this idea that the further along you go, the more accurate you are. And so you can use the beliefs that are sort of later in time. Those are more accurate than the beliefs that are earlier in time. You can use the later beliefs to fix the earlier beliefs. And you don't need to wait all the way until the end. Of course, when you wait all the way till the end, you have perfect knowledge. Like you actually know how long it took. So this is sort of a more accurate estimate, but the disadvantage is you have to wait the whole time for it to happen, and you don't get as many samples, right? You only learn at the end of the day, whereas here we had 5 opportunities to learn. Every time we made a step, we had a chance to learn. Yeah.
So to go back to the question of Alice,
Yeah.
when we said that, oh, if we use this method because we have information about Bob,
Right.
we're updating Alice some value closer to Bob.
That's right.
For
That's
some,
right.
constant alpha.
Mhm.
But with the 4 episodes as is,
Yeah.
we can only do that after the 4 episodes, right?
Right. So okay, I guess you could imagine it this way. Imagine that these 4 episodes just repeated over and over again. So like Alice, Bob, and Carlos are stuck in a time loop, and they always do the same 4 episodes over and over again. In a Monte Carlo estimate, you would get exactly the estimates you have over here. So instead of being like 2/3, it would be like 2n over 3n, where n is the number of times you've repeated it. But in the temporal difference learning world, you would literally converge to the thing where Alice is equal to Bob. And that's because every time you learn something, you would push Alice a little bit closer to Bob. And if you just repeat that over and over again, eventually Alice gets exponentially close to Bob. So I shouldn't say they're equal, but they will be equal within an e to the minus n. So Alice will converge to the value of Bob. Bob will be the value of half. Because for Bob, temporal difference learning and Monte Carlo learning are exactly the same, because the end of the episode happens after 1 step. And for Carlos, Carlos will also converge to a half. So in the temporal difference world, if you just repeat this over and over again, you will get that all 3 players have a value of a half. And you can see that because Bob has a value of a half, and Alice and Carlos, all they ever did was pass to Bob. Yeah, maybe we should write this down. Monte Carlo thinks 0 at half 2/3, and temporal difference learning, if you repeated it over and over again. There's a name for this, by the way. I don't remember what it is. You should look it up in the book. Taking a fixed data set and just running it over and over again. Replay learning or something like that. Would converge to all 3 players having a half. So you can think, do you think it's more fair to say all 3 players have a value of a half? Or do you think it's more fair to say 0, a half, and 2/3, given what we know? And I think a half is more fair. As a team, they scored half the time, every time. So that seems right. If you added in some, for example, maybe there's a 5th one where Alice has the ball and then they just immediately lose the ball, then you can say, oh yeah, Alice has a value slightly less than a half. But with the information we have, I think it should be a half. Yeah?
So what's more accurate?
I think the temporal difference learning is more accurate, right? I think it totally depends on your philosophy of what we're trying to do with the world and like how you see this, right? So if you run the Monte Carlo, you get this as the answer. And the Monte Carlo has the property that we're anchoring our values with like the real life thing at the end. So of course, if you repeated enough episodes, it would converge to something. The temporal difference learning, given what we saw, would give a value of a half to all 3 of them. And I think that's more accurate. In the limit, as the number of things goes to infinity, they should converge to the same thing. So if you actually repeat real situations over and over again and don't just replay these 4, they will both converge to something, the sort of like truth of what their actual value is given the real Markov chain that they're following, and it should be the same for both. So it just has to do with a finite set of samples, what's a more accurate estimate, do you think? Okay, and we're going to see that in a little bit. We can actually measure how they're doing. So we're going to do a real kind of like, so far we've only been talking in words and just trying to get the idea, and we're going to do a real estimate in 1 sec. Okay, great question. Anybody else for questions or comments about this? Okay, let's do an example. And the example I'm going to do is the Gambler's Ruin, the random Drunkards Walk, that one. Okay, what do I want? Temporal difference learning, okay. So, and so to start with, I programmed exactly what we did last class, but I programmed it with Monte Carlo for the Gambler's Ruin. And the Gambler's Ruin, if you remember, it's a guy who's going up and down, and there's a terminal state at the top and the terminal state at the bottom, and they're going up and down according to fair coin flip. In fact, this is the one we saw in the video, and that we're going to see in the video here as well. So it's going to be this one more time, right? So we're going to start somewhere in the middle. What's the probability we end up at the top or at the bottom? We did this problem last time, and we're going to do it with Monte Carlo this time. So here is the Monte Carlo method. It's a copy and paste of what we had with Grid World and the Roomba last time. And again, you have to keep track of the history. In this particular problem, unlike Grid World, I know the exact answer. So in Grid World, I didn't know the exact answer. But in this problem, because we did it already in Lab 1, the exact answer is the function x over n. And by using the exact answer, we can make these plots that look like this. So I can plot for different values of alpha. I can calculate the error and see how the error is going down as a function of the number of episodes. Let me zoom out a little bit. We could not do this in Grid World because we didn't know the exact answer. But for this one, we do know the exact answer. And you can see that as you change alpha, you get different things. Really small alphas shoot down to 0 or very close to 0 very quickly, but then they bounce around a lot. Whereas big values of alpha take longer to get to 0 and vice versa. Maybe I said that the reverse. Yeah, small values of alpha take a long time, but then they have small variation. Big values of alpha go down quickly and they have big variation. So this is all a repeat from last time. But I'm going to take the code, and I'm going to show you how to modify it to make it temporal difference learning. Questions about this one before we jump in? So let me show you the algorithm from the textbook. And the textbook gives you the algorithm before the example. Here is the algorithm. And this is called TD0. TD stands for temporal difference learning. And 0 means zero history. So we're just learning as we go from the exact next state. We're going to see later you can make variations on this TD to include more history than just one step, but we're going to do the one-step history. And what you do is, again, you simulate everything. So you start an episode, and you loop over all the things, but this time there is no history, and that's because you update immediately. So when you want to update the value of the state S, you only need to know the value of the next state, V of S prime. And so what you're doing is you're pushing, this is exactly the idea of pushing the value of S towards the value of V of S prime. So this line represents the arrow from this diagram over here. So pushing towards the next state that you see. And so unlike in Monte Carlo, where you have to keep a whole history of what happened and then kind of go backwards in time, once you finish, you can just do it one step at a time. And so the code ends up being much cleaner. You can do it right away. So let me show you what this code looks like for our particular problem. So this is the TD0 method. And again, we have the exact answer. But you start with any value function you want. And this is very similar to what we had before. Let's write in some comments as we go. So we're going to loop over some number of episodes. So this is just like the code that we had at the beginning of last class. Loop over some number of episodes. I'm going to initialize the state. So start somewhere. And we're going to keep going until the episode ends. So keep going until the episode ends. Okay, and just like in Monte Carlo, I don't know the rules of the thing. So I just have this gambler's ruin next state function that will tell me what is the next state. So get the next state according to I'm going to call it a black box, right? You don't need to know the rules of what happens. You just need some way to simulate what happens. And what I'm doing is before, when I did Monte Carlo, I was taking delta value. That was the difference between the end and what we had. So let me scroll up quickly just to highlight the difference between this. Let's call this one the TD learning delta value update. And I just want to compare it to what we had before. So I'm going to take this all the way up to, and I'm going to put it right next to the code for the Monte Carlo and show you what happens, what the difference is. So let's put this all in comments so we can look at the difference. Okay. Actually, let me move it. So it's just above this stuff. So in Monte Carlo, I have a history of what happened. I let G is the actual total return. It's the sum of all the rewards that happened ever. So G is what happens at the sort of the total reward you got at the final time. And then I do this update where I do the learning rate, which we called alpha, times G minus the value function of state. So I update the value function. I push it towards the final value. this is what we were doing in Monte Carlo, and that is exactly what is in this picture over here of pushing up towards the final outcome. So this final outcome, we called it G, and for every state along our trajectory, we push towards G with some learning rate with some alpha value. Let's compare that to the temporal difference learning. In the temporal difference learning, you do the same thing, except instead of doing G minus the value function, you do the value function of the new state minus the value function of the current state. So that is exactly the arrow on this side. The arrow between you and the next state, that is in the direction that you push. And you can also think about it, if you want, you can say, I'm estimating the value of G. The value of G is some unknown function. You can say, I'm just estimating it by value function of new state. That'll be my estimate for G, and that estimate will work. So all of this is comparing the Monte Carlo learning to the temporal difference learning. Let me show you in the actual code how it works. So you do this learning step after every single step, right? So I think another big difference is we're doing this, we're learning as we're going. We don't have to wait till the end of the episode. We can learn at every time. And then, if we finish, then we're done the episode and we start over. But that's the whole code. So you'll also notice that the whole code is a lot shorter because there is no part 1, part 2. So in the Monte Carlo, there's this part 1, part 2. First, you have to do all the simulations, and then you do these updates. In the temporal difference learning, it's much shorter because you're doing both at the same time. So you're learning as you go. You don't wait until the end to learn something. Okay, and here's what it looks like when you run it. So run this thing. I probably have to run all, or it will probably yell at me. Okay, it worked. So yeah, okay, let's try run all. Okay, any questions while it's running? What the idea is here? Yeah.
So I noticed this last night on the algorithm.
Mm-hmm.
It says the update is B of S gets updated some alpha times reward
Yes.
plus BS prime minus BS.
Right.
In your code,
Yeah.
you don't actually add any reward. I know it's set to 1.
Yes.
To 4.
Yes, okay, this is a great point. So in my problem, in the gambler's problem, the only rewards are these terminal rewards at the final state. If there were rewards along the way, you would have to add it on here. So you would have to put on reward now plus this, and then it would work. Maybe it's more clear I could just do that. So the reward at every step in the gambler's problem is 0. The only rewards are at the end, so you're adding the 0 on every time.
Right. So rather than setting the last index
Mhm.
as 1, in the episode, if I said, so like if current state equals 0 or
Yeah.
state and target, I would add like reward now is equal to 1, and then that gets updated.
Yeah, you could do it that way. So the way I have it right now is I just put in the reward at the final state. I put that in at the beginning. So I said the value function is 0 at 0 and the value function is 1 at 1. And then that way it knows the answer at the ends. So if you're one step away from the end and you step there, then you will learn it immediately through this thing, right? So if new state is a terminal state, then that'll be the correct answer. And then you'll do correct answer minus what you are now. That'll be the difference. Okay. All right. Other questions or comments? These are great. Okay, and you can see what happens when you run this. Hopefully it'll work now. So here is the Monte Carlo is in blue, and the temporal difference learning are all the other colors. And one thing you'll notice is in the very first episode, at episode number 1, the Monte Carlo value is quite large, and already the temporal difference learnings have all learned something, even after 1 episode. And that's because I'm plotting what is happening at the end of the episode. But remember, Monte Carlo only had 1 chance to learn. So it ran 1 episode, it learned 1 thing, but the temporal difference learning has a chance to learn at every step. So by the end of the first episode, the Monte Carlo is already behind because the temporal difference learning has learned something already. And you can see that it drops spectacularly fast near the beginning. So the Monte Carlo value is super slow compared to the temporal difference learning. You do have to be careful because if you make the alpha too big, then the temporal difference learning will bounce around quite a lot. But if you choose the value just right, then you get a better estimate than the Monte Carlo, and it can go faster as well. Another thing you can do is, like I said, you can always put alpha on a schedule, so you can start out with big values and then you go towards small values. In these pictures, the alpha is exactly how much of the arrow you want to do. So when you don't know anything, you want to take big steps towards new knowledge. When you already have pretty good knowledge, you want to take smaller steps towards new knowledge. So by putting it on a schedule, you can get the best of both worlds, but you can improve things quite a lot like that. So that's TD0, learning from one step. Okay, we're about to do TDN, learning from n steps, but this is a good place to stop for questions. Okay, let me show you guys the video for TDN. So in the video that we started the class in, they do TDN in a lot of detail. So let me show you TDN. And in fact, let's go all the way over here to the example they do. Okay. Okay, and another thing to remember is all of this stuff, you could say we're just learning the value function. Why is learning the value function useful? Well, remember last class we saw if you can estimate the value function for any policy, you can always do policy improvement and do this loop of estimate the value function, improve the policy. Estimate the value function, improve the policy, going back and forth. Okay. And again, this is what I mentioned. In Monte Carlo, you have to wait till the end, and that sucks. But in temporal difference learning, you can learn right away, and that can help. So let me run this example for you, or show this video with this nice example.
Now to visualize the adjustment to evaluation, I'll use a simple Markov reward process. We have 4 possible states, S1, 2, 3, and T, where S capital T is a terminal state. The possible rewards are the integers from -3 to 3, and there's no discounting. And just like in Monte Carlo, we don't get to know the distribution function. From here, we can visualize our sequence of states over time with this grid, and our rewards with this. Let me explain. I'll walk through an episode. For time t equals 0, we sample our first state, which happens to be S3. And then, with a distribution that depends on that state, we sample a pair of a reward and the next state. Then we do this again and again until the end of the episode. The reason I'm representing things this way is it makes sums of rewards clear. Each one of these horizontal lines indicates the reward accumulated so far in the episode. That makes it easy to picture the returns. For example, the return G3. It's just the difference between the levels at t is equal to 3 and the end of the episode. Next, let's remember our goal in evaluation. It's to estimate the value of each state, which we do with a table. We refer to that with a capital V. Now, what happens in constant alpha MC is we sample an episode to completion, then we'll apply this update rule for each time step of every episode. Let's see that for a few more episodes.
Okay, so this was the version of what was in the textbook picture of updating in constant alpha MC. You update towards the little
capital
arrow
V.
at the end, right?
Now, what
So you
happens
get
in
some
constant
information,
alpha MC
you have some
is
simulation.
we sample an episode to completion,
Maybe I skipped over the part
indicates
that I
the
wanted.
difference between the levels at
But yeah,
t is
so there's
equal to
this
3
arrow at the end,
and the
right?
end of
You
the
notice
episode.
the last value
Next,
G3,
let's remember our
and then
goal in
you
evaluation.
update all your estimates towards
It's to
that value.
estimate
Let's
the
see if I can find
value of each
where I did
state,
that.
which we
Okay,
do
let's
with a
VFS.
table
And then
See?
I want to do
update rule for
okay,
each
there's the
time
constant
step
alpha,
of
and
every
this is the
episode.
picture from the textbook, right? So you take the value you thought was happening at this state and you push it up so that it more matches this thing. So this kind of arrow is the direction you're pushing in the direction of this difference between what you thought and what you have, which I guess they have with a little orange square over here highlighting this value. Okay, but now we're going to see temporal difference learning on the same example. So this is kind of similar to the picture with the driving home, except it's a little more abstract, right? So instead of thinking about driving home, you have this abstract thing. I think if you want to think about it in terms of driving home, that's helpful, at least for me. So, and he's about to do temporal difference learning. When I showed it to you, we did it after one step. So I said, learn from the next step. He's going to do temporal difference learning with 4 steps. He's going to learn from 4 steps into the future. So I'll show you that.
Episode. Let's see that for a few more episodes.
Okay, so more Monte Carlo before we switch to temporal difference learning.
Now let's get into the temporal difference method. Let's say we just sampled this episode and we'd like to apply the update for the state at t equals 2. As mentioned, the issue with MC is that we need to observe until the end of the episode. So let's compromise that a bit. Let's say we just had to make do with only observing up until 4 steps after t is equal to 2, meaning we don't see the rewards beyond that point. The number of steps is an algorithmic input, so we call it more generally n. This means we need to update this in the update rule since it's only known at the end of the episode. We need to replace it with something. Well, we've observed some portion of the return, so we should certainly use that. The question is, what do we use in place of the unobserved part? Well, these things add up to G6, so we need something to approximate that. Wait a minute, that's exactly what our value function does. We can use the value of the last observed state as an approximation to G6. Here, the value is 0, but during the algorithm, it'll do the trick. And now we can see the TD method in action. Though, you'll have to forgive me, it's tricky to show the adjusted return like I did for MC a second ago on screen, so I'll leave that out. But outside of that, this is what it looks like to process a single episode. Notice how the value updates are applied within episode and are lagged by 4 steps. And obviously, this process repeats. Very fortunately, just like in MC, we ultimately converge to the right answer. Okay, let's now review this more generally.
Okay.
It's called n.
So in what I showed you guys, I was doing n equals 1, and in this example, it's n equals 4. So n equals 4, n is the number of steps into the future to look. So what's happening is we are updating what we thought happened at this time equals 5, using the next 4 steps. So by looking at time 6, 7, 8, 9, by using the next 4 steps, we can sort of take the information we have some idea that's more accurate as to what's going on at this time than was happening at that time. And by taking the information from the future and like pushing it back through time, we're improving our knowledge at this earlier time. That's why it's called temporal difference learning. So we're using the fact that the future is like more knowable than the past to import knowledge from the future into the past and update our estimate. And once again, we're updating by taking our value function that at this time, our value function for this state, state 2, and we're updating that value function to reflect what happened in the next 4 steps. So that's n equals 4 Monte Carlo learning. The one we did before, TD0, would be n equals 1. It's a little bit unfortunate that TD0, zero knowledge, is n equals 1, but that's just the way it is. And let me show you how this works in our Python code. So I implemented this one as well. TDN. So in the TDN, what you do is you have to run the same thing as before, and I have a little history here of the last n states. So this little list just stores the value of what happened in the past few states. So in sort of the picture that you see over here, we're storing, for every time, we're storing the last 4 things that happened, or the last n things that happened more generally. And then what we do is we learn using that. So here is the heart of the thing, the most important update rule that gets applied over and over again. We look at the state n steps ago by pulling it off of the list of the states, and then our delta value, it's the current state minus the state n steps ago. So in Monte Carlo, you wait until the end, and then you go back in time. In temporal difference learning with n steps, you go n steps into the past, and you update the value function n steps into the past. You do have to do something a little funny to deal with corner cases, like what happens right at the end and things like that. But this is the core idea. Go back in time n steps and update from there. And if you run the thing, you will see some plots like this. Depending on the value of n, you can get more and more different things. If n is infinity, if you make n really, really big, then that's just Monte Carlo learning. You wait until the end of the episode to update anything. For other values of n, you get different curves. And there's a whole kind of like thing you can do. You can play around with n and alpha to see what is the best. And that's actually what they do in the rest of this video, or in the next couple minutes of the video that I'll show you. Okay. So they're going to write it out in a second. But any questions or comments so far? Okay, so we're going to see them play around with the n and alpha values a little bit, and then we'll
Okay,
sort of know
let's now review this more generally. It's called n-step temporal difference learning, and it's easiest to understand if we recall the Monte Carlo approach. where we used this update rule for evaluation. To be clear, this refers to the state at time t of the nth episode. Now in this rule, we call this the target. It's what we move our estimate towards on each step. In n step td, we replace the target with this, which is the sum of discounted rewards between t and t plus n, plus our existing value estimate to approximate the remaining rewards, discounted by n steps. The reason we do this is because that's what's observable at time t plus n. Also, things are appropriately set to 0 when t plus n is beyond the end of the episode. Now let's talk about n. As mentioned, it sets the lag between the time of the state whose value is being updated and the time of the most recent observation. And it's worth emphasizing, just like alpha, n must be specified up front before you run the algorithm. If you set this integer to 1, the algorithm is very eager to make updates. Values are updated after each individual reward. If n is infinite, then td is identical to mc, since the delay is always greater than the episode length. Also, some terminology. Using a value estimate in the target is called bootstrapping. As we'll see, bootstrapping has major implications. So let's see that by comparing its performance to MC on a pure evaluation task. That is, the random walk example from the previous video. To refresh, it's a Markov reward process with 7 states, 2 of which are terminal. All rewards are 0 except when transitioning to the upper terminal state, in which case it's 1. Also, no discounting. The initial state will always be the center, and each transition is a 50-50 chance of going up or down. So one episode looks like this. As a reminder, when doing evaluation, the goal is to estimate the expected return from each state. Like last time, we can show the true values like this. Our algorithms begin by initializing estimates at 1/2, and we can measure performance using the absolute difference between our estimates and the true values. To keep track over time, we'll plot the average absolute difference over the number of episodes processed. To demonstrate, I'll run Monte Carlo with alpha equal to 0.03, which looks like this. Hopefully, this is nothing new. Okay, now we can see TD. I'm going to use an alpha of 0.1 and an n of 1, which gives us this. It looks like TD does a better job, certainly in the short term. But this isn't a complete comparison. The randomness of a single run and the specific choices of alpha and n make this view a bit too specific. So let's try something different. I'll use the same plot of error versus episodes, but this time I'll include sliders for MC's alpha and TD's alpha and for TD's n steps. But keep in mind, n is an integer. Here I'm starting it at n equals 4. A few other changes. Instead of using 7 states, I'll use 11. This will allow us to investigate a larger range of n's. Also, instead of running the algorithms just once, I'll run them 200 times, which will give a whole distribution of performance. For instance, this is the performance of MC, where the line gives the performance averaged over all 200 runs, and the band is plus minus 1 standard deviation. And now for the punchline. This is what TD's performance looks like. Not only does it do better faster, but it has a tighter, more certain distribution of performance. At least for these choices of alpha and n, TD performs better and is less risky. Now let's move around MC's alpha. As we can see, and as we already expected, over a certain range, a higher alpha makes for better early performance, but makes performance quite noisy in the end. Let's freeze this at an alpha that performs well. Now for TD. The first thing to recognize is that if we set n to a very high value and change alpha to be the same as MC's, TD is identical to MC. So TD includes MC as an option. But if we set n to 1, then we could do a lot better by increasing alpha. This is because a small n reduces the variance in the updates, so you can afford to take larger steps. Okay, now just to get a feel for the space of behaviors, I'll cycle through a few n's and for each, vary the alphas. Hopefully this gives you a sense of how performance can change as we vary these knobs. And if you'd like to explore this more, I've linked a code in the description you can use to play with this. There you can find a more fleshed out discussion of these two algorithms from this angle. But now, let's try a more direct perspective for viewing TD's trade-off between n and alpha. What we'll look at is the average error after 10 episodes. What I mean is this. Here, we have alpha along the horizontal axis and n along the vertical axis on a log scale. Using colors, I'll show the average error after processing the 10th episode. For example, this is what errors look like for n equals 8. I've normalized the errors to have a value of 1 when they have achieved their best value for a particular n, and that's colored as blue. That means around here, we achieved the best performance for n equals 8. Now, if we do that for the remaining values of n, we get the full picture. Clearly, for lower values of n, best performance is achieved for higher values of alpha. So we see there's an interdependence between n and alpha for achieving good performance. Still, observing performance like this doesn't explain why they perform differently. Sun and Bartle's book has a very interesting way of explaining it. The argument goes like this. We'll compare MC to one-step TD, and we'll adjust their algorithms slightly by using batch training. I won't go into the details, but the important thing is a fixed batch of episodes.
So batch training is exactly the Alice and Bob example we started with today. So if you have those 4 episodes and you repeat them over and over again and you put them in the algorithm, that's called batch training. And he's about to repeat exactly what we said, that if you have this Alice and Bob example, you will see that Alice and Carlos and Bob should all have a value of about a half, which is what you would get for batch training with temporal difference learning. They would all have a value of a half. Whereas if you do Monte Carlo learning, then Alice has a value of 0, where Carlos has a value of 2/3 and Bob has a value of a half. And I think the temporal difference learning is more realistic. But again, you have to decide when you have incomplete information, what does it mean to have the best possible estimate? Okay. Any questions about any of that from the video? So I think he did a good job of showing you the trade-off between the n and the alphas. In real life, people kind of just try a bunch of values and see what is working the best. So you do have to set these values of alpha and n, and it is up to you what you want to set them to. Okay, maybe I'll stop there for that. Any questions or comments about any of this stuff? You should really think of temporal difference learning as like a better version of Monte Carlo. You don't wait until the end. You wait some number of steps. And if you wanted to wait until the end, you would just set n very large. That would automatically do Monte Carlo. To me, this is the first like real reinforcement learning algorithm in the course. Everything else so far has been kind of like basic. Monte Carlo in particular, you just wait till the end. Anybody can do that. But this is like a real amazing trick that works quite well. Yeah.
Back to that, the updating the value function.
Yeah.
He said alpha times GT minus the
Right.
value function for the previous state or
Mhm.
state, and for n for TDN.
Yeah.
That would be.
Yeah. Here, I can show you the line in my code. It's right here. Yeah. Okay.
And then what was I gonna say? I lost it. No. Okay. So the GT value, the
Mhm.
G value, that's the sum of all rewards
That's right. Yeah.
plus gamma discounted
Yeah, it's the total, the quote total return. So the sum of all the rewards,
up to that state.
well, the sum of everything into the future. So from a certain state, how many rewards do you expect to get all the way up until time infinity? That's called the total return. So that's the G. And
I see.
okay, it's true. So again, because I'm doing an example that only has terminal rewards, the entire return is included in the value function.
Look at that one.
If you have something that has ongoing rewards, then the value function between time 0 and time 4, you need to also include all the rewards you got in that little time interval. So I think when they did the thing, they had like reward 0 plus reward 1 plus dot 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 plus reward n. So the value function of where you are now, I guess you're like, this is like a back to the future. Right? This is the past, and this is now, right? Okay. And the value where we are now, plus all the rewards we got in the last few steps. Maybe I should call them -1 up to -n. Let's call them like that. Reward 1 step ago, reward now, reward 1 step ago, all the way up to the reward -n. So if you want to know, you take all the rewards here, so reward -1, reward -2, reward -n. And we can update our value for what happens n steps ago. Step -n versus s now. So the difference should be s -n plus all the rewards we got in the little intermediate time. That is a better estimate for S0, or vice versa. VS0, which is the return starting from now on to infinity, plus all the rewards here is a better estimate for VS -n than our current estimate, right? So by looking forward in time n steps, we get a slightly better estimate, and then we can improve our current estimate by moving in that direction a little bit. Yeah, so it's true, you do need to add on these reward things to make it correct.
I guess intuitively in my head, I thought it was the sum of all the values up to, but it's not.
No, yeah. So you should think of the value function as like estimating the expected value of something that happens like into the far future, right? Like the total reward into the far future. For like a chess game, right? It's like you have some position in the mid game. The value is what is the chance you're going to win the game at the end of the game. So you usually don't want to add up value functions. Things like taking their difference, that makes sense. Yeah. Okay. All right. Any other questions or comments? So I had sort of on the schedule was to go over the lab and like put the results. But I think not everybody is here today. Why don't I'll just record that and I'll post it for you guys and we can finish a little bit early and then people can watch that on their own. I think some people had no problem with it at all. Some people worked really hard and then eventually got it. So great job. I will say, even if you got it correct right away, I saw a lot of people's code have like a lot of for loops and stuff, and a lot of them are like one-liners if you set up the right matrices. So when I post the right answers, you will see that you can do things quite quickly if you're good at matrix operations, and I'll try to explain that as well. Of course, it's not incorrect if you did it with loops. I think it's better for you to understand how to do it with loops first, and then you can like learn the cool matrix way. But it is a good skill to have. So check that out anyway. And I'll just post that as a recorded video. I think that'll be more useful to people, and we'll stop a little early. Okay, any last minute questions or comments? Okay, I'll be here for a bit if you want to come chat. Otherwise, see you guys on Tuesday.